talk will feature one of the recent advances in the field of spin rectification in boundary-driven quantum spin chain. Co-chairing the session, I would like to invite Dr. Nasan Wagi sir, one of our faculty members, the man who constantly extends the love and support to all high prospect of physics department. Over to you, sir.
Okay, thank you. A warm good morning to one and all. Respected speaker of this session, Dr. Vinitha Balachandran, faculty from various colleges, research scholars, and dear participants. First of all, I welcome you all to the second session of the second day of our International E-Conference on recent advances in physical sciences. Today, for this session, we have an eminent resource person, Dr. Vinitha Balachandran, from Singapore University of Technology and Design. It is my pleasure and privilege to introduce our speaker, Dr. Vinitha Balachandran. Dr. Vinitha Balachandran is currently working as Senior Research Fellow in Dario Politics Group in Singapore University of Technology and Design. Her research expertise is in quantum transport for applications in thermoelectricity, quantum computers, quantum chaos, and many-body computational physics. She obtained PhD in physics from National University of Singapore under the supervision of Professor Guo Jiangli. After PhD, she did her postdoctoral research with Professor Giulio Casati and Professor Giuliano Benetti at the University of Insubria, Italy. In 2015, she joined Singapore University as a postdoc. With immense pleasure, on behalf of Department of Physics, Bharat Mata College, and Stride MG University, and invite Dr. Vinitha Balachandran to deliver her lecture on the topic spin rectification in boundary-driven quantum spin chains. We welcome you, Dr. Vinitha. Over to you.
Thank you, Nasan. Hope you can see my screen now.
Yes.
Okay. So thank you, Nasan, for the nice introduction. So I'm Vinitha Balachandran from Singapore University of Technology and Design. And today I'm going to talk about spin rectification in boundary-driven quantum spin chains. And first of all, I would like to thank the organizers for giving me an opportunity to present my work here. And okay. Okay. So I work as a senior research fellow in dynamics and thermodynamics of quantum system and devices group by Associate Professor Dario Politi in SUTD. And so I'm currently working on three main research areas. The first one is the quantum transport. So today's talk is related to the studies on quantum transport. So here we try to propose technological devices that make use of quantum effects. And currently we are focusing more to the thermoelectric applications. And also I had the wonderful opportunity to work with Giulio Casati, who is the pioneer in the field of quantum chaos. So this field has been quiet for a few decades now, but recently, there has been a revival in this field of quantum chaos in relation to the measure called the out-of-time ordered correlator, or called the AUTOC. So this AUTOC is a measure used to, is related to Lipton exponent in classical chaos. And recently, it was shown that it can also be used to measure the information scrambling in...
Recording in progress.
Information scrambling in black holes. And since then, not only in the quantum field theory, but also in other areas of the physics, people are using this measure. And at present, I'm doing a few projects related to like characterizing the quantum many-body dynamics using this measure of AUTOC. And also like I'm working on machine learning. So here we try to apply insights from physics to improve the efficiency of the learning process. So as you all know, it's very difficult. Like there are only a few models that can be quantum models that are analytically solvable. So computationally, like if you are trying to study large quantum system, it's very hard because you have a very large Hilbert space dimension, and you can use the DMRG or the tensor network state methods. But the problem is like if the system has very large entanglement, this method fails. So recently it was shown that the neural network quantum states can efficiently represent the quantum wave function, and it can overcome the limitations by this caused by the entanglement. So at present, we are also working on this, like in this direction, to use the neural network quantum states to study large quantum systems. Okay, these are the the work I'm currently doing. So more details can be found on this website. So these are the few papers I have related to rectification. So because of the time constraint, I won't be able to go through all of them. So I will just go through some of the key results. So I will mainly focus on the first one. That's a perfect diode in quantum spin chains. And I think it's the simplest one. And if you follow this, it's very helpful to follow all the other papers. Okay. So before starting the talk, I would like to acknowledge my collaborators. So Giuliano Benetti, Emmanuel Pereira, and Giulia Casati, those were the ones who introduced this topic to me, the topic of rectification. And also, they were also the first, the co-authors of my first few papers on rectification. And Go Chu was a PhD student in our group, and he's currently a faculty in China. And Stefan Clark and John Gold are the one who I collaborated for my studies on rectification using mobility edges. And Kang Hao is a PhD student in our group, and he's currently doing all the numerical works related to this rectification. And Ryan was also a PhD student. And Dario is my mentor and PI in SUTD. Okay, now I'll start with the talk. So rectifiers are the devices that allows the current to flow preferentially in one direction. So the simplest example is a PN junction diode. So I think everyone is familiar with the IV characteristics of the PN junction diode. So here, when the diode is forward biased, that is, you have the P region connected to the positive terminal and the N region connected to the negative terminal, and a large current will flow through the diode. And when we reverse the polarities, so we have the reverse bias, and ideally no current should flow, but usually we see some current. So this is a PN junction diode, is a rectifier. Like it rectifies the current in the reverse bias. Okay. So this rectifier, the PN junction diode, rectifies the electric current, so which is due to the flow of electrons. And here we make use of the charge degree of freedom of the electrons. So, and all the electronic devices are based on this charge degree of freedom. But the electron has both spin and charge degree of freedom. And you can think of the electron spinning in clockwise direction as having the up spin, and in the anti-clockwise direction as having the down spin. And spintronic devices are the devices that make use of this spin degree of freedom. And so you can, similar to the flow of the electrons, you can think of the flow of spins and can like define a spin current. So in the electric current also, like the electron has both spin and charge. So when we talk about the electric current, when the electron flows, it's also the spins are flowing. But what happens here is that you have equal number of up and down spin flowing in the same direction. So they just cancels out. So in the case of the electric current, you will only see the effect of the charges. But you can have, if there is a polarization, spin polarization bias, then you can have the upspin moving in one direction, whereas this downspin moving in the other direction. So you can have a net flow of spins, and thus you can have a spin current. So there are some materials where you can have the interaction between both charge and spin degree of freedom, but I'm not talking about this today. So this is, in my talk, it's just about the pure spin current, just due to the flow of spins. Okay. So the spin-based technologies are already in the market. So some of them are like TMR sensors, tunnel magnetoresistance sensors, or the MRAM devices, the magnetic random access memory devices. And so with the increased miniaturization, we are forced to rely on spin-based technology. And for the spin-based technology, so the building block or the fundamental unit is a spin rectifier or a diode. So in this talk, I'm going to describe one of our proposed model for perfect spin current rectification. Okay. So for the PN junction diode, we know that we apply the voltage as the bias. So similarly, for the spin current rectifier, the bias is provided by a spin polarization difference. So if we have a quantum system that has a spin, so the bias is provided by two baths at the two ends. So we call this system as a bath because it's something very larger than this the diode, and it can have a continuous supply of the spins. So for instance, in this left spin bath, as I have drawn here, the spins are in all the directions. So this is an infinite temperature bath. So if you connect this bath to the quantum system, then the system will be driven to a state in which you have equal mixture of up and down spins. Whereas in the right bath, so I have put all the spins in the down state. So it's a bath which can supply spin down spins. So if you connect this bath to the system, then this will drive the system to a state in which all the spins are in the down state. So we provide, so the bias is provided by like this. So as you can see, there are more number of the up spins in the left bath compared to the right bath. There is no spin in the right bath. So there will be a flow of the current. If you take the up spins as a reference, so there will be a flow of the up spins from the left to the right. So we call this as forward current. Now the reverse current, so in the reverse bias, for the PN junction diode, we exchange the polarity. So we do the same thing here. So we exchange the polarities. So we put the spin bath with all the down spins to the left side and the infinite temperature bath on the right. And so here, now the current will flow from right to left, and we call this as the reverse current JR. So the rectification can be characterized by this measure R, which is a ratio of forward current to the reverse current. And so when R is equal to 1, so this means that the forward and the reverse bias current are the same. This means that the system cannot distinguish between the forward, like whether you put the bath on the left side or on the right side. So that means there is no rectification. But if you have a perfect rectification, that's you need, for instance, in the PN junction diode, the reverse current is rectified. So the reverse current will be 0 for an ideal rectifier. So if JR is equal to 0, you can see that R will be equal to infinity. So that's a limit for the perfect rectification. And because this is a quantum system, you can have like a current in the reverse direction, but the forward current be 0. So that's the case for R is equal to 0, and that's also a perfect rectifier. So you have a current in the forward reverse direction, but no current in the forward direction. So these are the two extreme limits of rectification. Okay, now there are also other measures in the literature where you can measure, like characterize the rectification. And so one such measure I will use in my study is a contrast. So it's defined like this. So as I said earlier, when there is no rectification, forward and the reverse bias current will be the same. So here, when they are the same, the numerator will be 0. So the C is equal to 0 means no rectification. Whereas for the perfect rectifier, one of the current in one of the bias should be 0. So if one of them is 0, so you can see the C will be 1. So these are the two limits for the C value. C is equal to 0 means no rectification, and C is equal to 1 means perfect rectification. Okay, so I'm considering a spin chain model. Spin chain means the one-dimensional array of spins. So the general Hamiltonian can be written like this. So here the sigma x are the polyspin matrices, and the alpha means the site index. So here the first spin is called the spin at L is equal to 1, and the second one is L is equal to 2, etc. And as you can see, there are only interactions between L and L plus 1. So the next, just the nearest spins. So, and J is the tunneling strength. That's the strength at which a spin can flip from one side to another. And this delta is the interaction strength. That means the two nearest spins can interact with each other. And the strength of this is this delta. Okay. And if you read the papers on quantum spin chains, then you will always see these terms like XXC chain. So XXC means that you have the couplings in X and Y direction the same, and then the C direction it's different. So it's called XXC. And if it was the same, if delta was equal to J, then you will call it XXX chain. And if like X and Y were different, you will call XYC chain. So these are the different terminologies that you can find in these quantum spin chain papers. And so this is not a theoretical model. This can be physically realized. This Hamiltonian can be physically realized. So it can be realized in solid state materials like this. So this is one such material. So, okay, you will think that this is a three-dimensional material, but here it can be treated as one-dimensional because the interactions in the other two dimensions will be too small that you can neglect it. So you can consider this as a one-dimensional material, although physically it's three-dimensional. So, and thanks to the technology that we have in the current laboratories, that we can also physically realize this XSE chain using ultra-cold atoms. So this is one of the setups. And there are also other setups using the optical microtrods, so superconducting circuits, and even you can simulate this Hamiltonian in quantum computers quite easily. So now I'll explain the methods. So the time evolution of the system is described by Lindblad master equation. So this is the equation. So this was put forward by Lindblad, Gurini, Kasovsky, and Sudarshan in 1976. So unlike if you have just a quantum system, you can describe it using the wave function. But since once you connect it to the baths, then the dynamics is not at all unitary. So it's a dissipative dynamics. And because of this, you need the density matrix to describe your state. So this rho is the density matrix. And this L is called the Lindbladian operator or Lindbladian matrix. And here, this term defines free evolution. Free evolution means that just the evolution of the system. So it doesn't take into account the baths. And the effect of the bath is described by this term. So this term is given by this equation. It's not very complicated. So if this gamma is the strength at which these two systems are coupled, like the bath system coupling strength. And the lambda. So the lambda is that what the polarization bias which bath imposes. So lambda is equal to 0 means if this bath, how to get this bath is using the lambda is equal to 0. So if you use lambda is equal to 0 and connect this bath, then this means that your system will be in a state with all down state. Whereas if you need a system, like your system to be in all up state, then you have to put lambda equal to 1. Whereas if you put lambda is equal to 0.5, then you will get an equal mixture of up and down spins in your system. So this is how we manipulate, like how to get the effect of the baths in this equation. Okay. Okay. So I think I have written the boundary-driven quantum spin chain. So boundary-driven means that, as you can see in this, this n is takes a value only 1 and n. So the 1 means that the bath is connected to the first spin, and the n means that the bath is connected to the last spin. So the baths, we connect the baths only to the boundary. So we are driving the system by the baths at the boundary, and that's why this is called the boundary-driven quantum spin chains. Okay. Okay, now I explain how we calculate the spin current. So the spin current can be defined by continuity equation of the local spin. So the change of these local spin defines the spin current. So if we have Ji is the current entering the site I and Ji plus 1 is the current leaving the site I, we can define this continuity equation similar to the probability current equation that we study in quantum mechanics. So then using the Heisenberg equation of motion, you have to just substitute for which Hamiltonian that you are using. And since we are using an XSC chain, if you work it out, we will get this expression. And this is a expression that we use to simulate like how to calculate the current in our studies. So at the steady state, the spin current will be the same at all sides. So I'll explain what is the steady state in the next slide. Okay. So the steady state means like when you have a quantum system and then you connect the baths and then you try to measure some observables, say you are measuring the spin polarization, then you will see that it has some initial value. Then this value changes in time. And after some time, if you wait for long enough time, then it will reach some equilibrium value. And this, when you find that the observable does not change with time, then the system has reached the steady state. And when you read the papers related to this driven spin chains, then you will always see this non-equilibrium steady state. So non-equilibrium steady state means that the system is reached far from equilibrium. Okay, so this is a equation we are trying to evolve to study the system. So the finding steady state means that this has to be zero because this state shouldn't change with time. So that means this is to be zero. So to find the steady state means you have to numerically solve this Lindbladian matrix. So this is a matrix of 4 to the power of n times n. And this, if you diagonalize the matrix, then the steady state is the state with the eigenstate with 0 eigenvalue. So this is one way of studying the system. And also you can do the Runge-Kutta evolution, time evolution using, so here now the matrix size can be reduced. But the problem with both these methods is that you can only like study the systems of like 8 spins because the memory you require to handle these large matrices is huge. So, and also for the Runge-Kutta evolution, you save some memory, but the problem is that it takes long time to reach the steady state. So because of this, we usually use tensor network based algorithm to study large systems. So a good review can be found in these papers. Okay. So there are some minimal ingredients to obtain rectification. So in this paper, they give these 2 sufficient conditions to get the rectification in the system. So the one is broken reflection symmetry, and the other is the non-linearities in the system. Okay, so these 2 conditions can be satisfied if there is the system and the bath are of different types or different statistics. Statistics means that you use the fermion for one bath and then the bosons for another bath, something like that. So this is one setup where they use the heat current, where they propose as a heat current rectifier. But so you can see they use 3 different types of materials like N1, N2, and N3. So that's how they get this rectification. There are also possible to get the rectification. These can satisfy these conditions using a geometrically non-reflection symmetric system. So one such example is this one. So as you can see, this is non-reflection symmetric. So if you connect a bath here or you connect here and you interchange, is going to be different. So when you measure the current. So, and we are trying to use this idea for our perfect diode setup. Okay. So now I'll explain our perfect spin diode setup. So we use a segmented XSC chain. The segmented means that it is divided into 2 halves. So the first half is XSC chain. So there is interactions between the spins in this left half. And in the right half, we take a non-interacting chain. So there's no delta term here. That means there's no interaction between the spins. Okay. Now these are the baths we use for this setup. So an infinite temperature bath in the left and a bath with all the spins in the down state in the right. Okay. So these are the results that we obtained. So here I have plotted the current versus the interaction strength. So the left panel is for forward bias and the right panel is for the reverse bias. So the different lines corresponds to the different system sizes. So as you can see, as you increase the system size, the current decreases. This is the case in both like reverse and the forward direction. And also we see that the current decreases as we increase the interaction strength. So it's the same in both cases. But the difference is that if you check the scale, the y-axis, scale of y-axis, you can see that the forward current is much larger than the reverse current. So it's almost of the order of like 100 or 1,000. Like as you increase the system size, you'll get more than 1,000 order difference. So here now I will explain the values of rectification that we obtain using this method. So here the left panel is for this R value and the right panel is for the C. So as you can see that as we increase the system size, the R value, like we get almost like 10 to the power of 4. And for large anisotropy. So for small anisotropy is always very small, the rectification. And if we compare the contrast, so we see that for as we increase the system size, especially from like 6 spins, we see that a sharp change in the contrast. So as you can, I have plotted a two vertical lines to see the transition. So we found that the large rectification can be obtained after this critical point. And recently we have a paper in the archive. So this paper is under review. It's not published yet. So we show that at this point, there is a non-equilibrium phase transition going on in the reverse bias. So it doesn't come at the forward bias. And so this sharp change in this rectification is due to this non-equilibrium phase transition. So this is called the non-equilibrium phase transition because, as I said earlier, phase transition is reached far from equilibrium. So the usual phase transitions that we see is this ground state phase transition where it's the equilibrium phase transition. So it's similar to the equilibrium phase transition, but it's just that you find it in the dissipative system rather than the Hamiltonian system. So in Hamiltonian system, we say that there is a phase transition when there is a closing of the energy gap. So here there is it's a similar concept. So we diagonalize the Lindbladian operator, and these eigenvalues are called the rapidities. And so, as I said, the first rapidity with the 0 value is the steady state. And the second one, there will be a gap between them two. But at the phase transition, this gap will close, leading to a phase transition. And so we found that this sharp change is due to this phase transition. And you can find the more details in this paper. Okay. So when you read the papers about the quantum transport, usually you see 3 different keywords. It's a ballistic transport, diffusive transport, or the insulator. So the ballistic transport, it's similar to the ballistic missile, that it's a transport in which there is no resistance. So even if you take a small system and then increase this size of the system, then you measure the current, it will be independent of the system size because there is no resistance. So if you plot the current versus system size, it will be just a constant value. So the current is independent of the system size in a ballistic transport. Whereas in a diffusive transport, so the current will, there is resistance. So current will decrease with time. So if you have a small system, it will have only less resistance. But as you increase the system size, the current will decay because there is more resistance. So usually if you plot the current versus the system size, it will be inversely proportional to the system size. And you can have a subdiffusive or super diffusive transport. So subdiffusive transport means this the power of the L will be greater than 1, whereas the super diffusive means it will be something between 0 and 1. So these are some of the terms that you will see when you read the papers about these quantum transport in boundary-driven quantum switches.
Recording in progress.
So if we connect these two segments, a spin here can flip to the other regime if the energy excitation on the left can be matched with the right. And we see that as they are of the same order, they can always be matched for the forward bias. And so we always see a transport or the current in the forward bias. Okay, now consider the reverse bias setup. So in the reverse bias, we just change the baths. So now here, the left half has all the spins down, and the right half has this infinite temperature state. Now the energy excitation on the left can be only at most, at least it will be of the order of delta. Whereas here, it can be only at most the J, because it's a non-interacting chain. There is no delta term here. So what happens is that for large delta, there will be a gap. So you cannot match the energy on the left with the right. And because of this, there won't be any transport of the current in the reverse bias. And the system will turn to insulating. So this is a physical mechanism that causes this insulating behavior or the in the diode. So we will see some numerical studies that confirms this. So here I have plotted the excitation spectra for a chain of 10 spins. So I have 5 spins in the left half and the 5 spins on the right half. So here the red lines are one for the excitation energy on the right. So there are 5 lines corresponding to the 5 spins. And here on the left, on the right, I have the blue lines. This correspond to the XC chain. So it's independent of delta. That's why you see a straight line for the Texas case. Okay. So if we connect this and then measure the contrast. So if we connect it with some very small coupling, so you can see all these resonance. So I have this dips of in the contrast, I have masked it with whenever there is a crossing in between these blue and the red line. So whenever there is a crossing means that the energy in both left half can be exactly matched with the that on the right. So there is a resonance, and because of which the contrast will decrease because there is always a transport in both directions. But the interesting thing is that if you consider this, after this vertical, the last vertical line, around 2, then there is no crossing. And we see the contrast just goes to the perfect rectification values, which is close to 1. So we find that the contrast is always large and there is no matching between the excitation spectrum. And so this is a plot that I have shown you earlier. But so you have so as you can see, this vertical line corresponds to this value, and after this, for all the system sizes, you will see that the value of the C is very large. And okay, you will be wondering why I could see a lot of peaks here, but this one is a smooth one. So this is because here I'm using a very small value of the coupling between the 2 segments, but here I'm using a large value. So all these small fine structures disappears when you have a very large value of the coupling between the 2 segments. Okay, so this is a critical value, and in this paper we analytically predict, by solving the excitation spectrum of the 2 halves, we analytically predict this value in the thermodynamic limit. So this is for the thermodynamic limit, but interesting thing is that even for system size of 8 and 10, this matches exactly with the value that we predict. And we also showed that so because this predictions is for thermodynamic limit, this shows that we can have a perfect diode in the thermodynamic limit. So thermodynamic limit that when n tends to infinity, you have a infinite number of spins in your system, or you have a very large system. So we see that there is we can get a perfect diode in thermodynamic limit after this critical interaction. And this is much more, our work is much more interesting in the sense that there were proposals for the rectification previously, but always when you increase the system size, the rectification decreases. But what we found that the rectification increases as we increase the system size, and I think that that was one of the most interesting things that we had in the paper. Okay. So now we also studied like how robust is this perfect spin diode to the perturbations. So in the segmented XXC chain, we try to put the interactions. So earlier we didn't have the interaction on the left side, right side. So now we are putting the interactions on both sides. And so this is a Hamiltonian. So we are just changing this delta value on the two sides. And also we considered like next nearest neighbor tunneling term. So what does it mean is that we have a term like this. So you can see that there is a coupling between L and L plus 2 spins. So it can couple the next nearest neighbor spins. So you can imagine it as to be in a triangular lattice where a spin can couple to the nearest as well as the next nearest neighbor spins. And also we put the staggered field in the chain. So staggered field means like you put a field in one side in one direction, in the other side the other direction. So, and we studied how far this perfect diode will be stable. So these are the results that we have for this general XSC chain. So this here I have plotted the rectification versus interaction strength. So the red line is for the 10 spins and the blue one for the 8, and then the green is for the 6 spins. So as you can see, as we increase the system size, the rectification value increases. And also similar to that of the perfect diode paper, we have perfect diode model, we have as you increase the anisotropy, like the interaction strength, there is a large rectification. So more details can be found in this paper. Okay, so for the perfect diode model, that's XXC chain plus XS chain, there is always a critical interaction strength. So this value beyond which the system is insulating. And this value is independent of the system size. So you take any system size, then this value is the same. But we found that when we add perturbation, then the critical value is dependent on system size. Actually, it increases with the system size. So this is a plot we have for the critical interaction strength when we add the perturbations. So the green one is for delta is equal to 0.5. So we have the interactions on both sides, and this is a value, and this value on the left we change the value, and we see how the critical interaction strength means that the interaction strength beyond which your system is insulating. So that we found that it increases with the system size. And as we increase the system size, as we increase the interaction strength, we found that this rate of increase is decreased, but even for very large interaction, we see that there is an increase in the system size. And this yellow line is for the analytical prediction. So we did the same thing like the perfect diode model. We tried to match the energy on the both halves, and then we could get an analytical prediction for this value. And then so our numerical values exactly matches with our analytical predictions. But what we see is that we won't be able to get a perfect diode in the thermodynamic limit. So always in the thermodynamic limit, you need an infinite, you need an infinite interaction strength to get the system insulating. And this increase in critical value can be explained using the increase of the width of the energy band when we have interactions or other perturbations in the system. Okay, so more details can be found in this paper. Okay, now I will summarize the talk. So I have discussed how spin current rectification can be obtained using boundary-driven segmented spin chain. And we showed that we can obtain the perfect spin diode in the thermodynamic limit using a segmented XZC plus XX chain. And the mechanism of rectification is due to the mismatch of excitation spectrum of two halves. And we showed that this rectification is robust to perturbations like magnetic field interactions or extra tunneling terms. But okay, we won't be able to get a perfect diode in the thermodynamic limit with these perturbations, but we see a very giant rectification even if there is perturbation. Okay. And yeah, my other works on rectification are using the same setup for the heat current or using the other concepts like the mobility edges or ferromagnetic domains. So which you can find in on my other papers. So I don't have the time to discuss it in this talk. So yeah, thank you for listening.
Okay. Thank you, Dr. Vinitha. Thank you very much for the wonderful lecture on spin rectification, boundary-driven quantum spin chains. So now it is the time for interaction. Participants, you can raise your questions directly or you can type it in chat box. There is one question.
Okay. So the question is, what are the advantages of spintronic devices over electronic devices? Okay, here's the next question. So as I said in my motivation, one of the thing is the miniaturization. As we go reduce the system size, we are forced to like use the something that that can like that has only like yeah, I think the miniaturization is one of the main advantages. Like we can store more things. Like if in the environment or you use the spin technology, you are able to like increase your storage capacity, and also I think maybe something that we are trying to study is also this reducing the heat effects, like thermal effects. There is always quite a lot of the heat based, and we are trying to use this spin based technology so that we can like control this the waste heat.
Okay, I have one question.
Yeah, sure.
How could you measure the reverse bias current with the system size? Is there any experimental setup?
Oh, okay. All these are the numerical setup. It's just like, yeah. So here, usually the providing the best, I think it's easier. You just like change the the bars. Like you assume that you have a system, and then the bars, all these are different systems, and then you change the baths. Okay, I don't think there is any experimental group that has done this exactly, but these are some theoretical proposal, like how can we do this?
Okay, thank you for your wonderful lecture.
Yeah.
Okay. Over to.
So I stopped sharing. Okay, somebody else.
Yeah.
Okay, explain a little bit of quantum computers. So I'm not very sure what was this specific about. Like this spin, I think whatever I did, my PhD was on like quantum information processing using spin chains. So if you take the quantum computers, like most of these gates are is using the spins, like you can. So once you study the spin chains, it's quite fundamental. You can apply to everything. So you can see any X gate, or this all are polyspin matrices that we are using. So in the sense that whatever these studies are like, it applies to quantum computers also. And yeah, I don't know what else. So whatever this study is related to the spin, you can think of the spin as a quantum bit, qubit, like how. So yeah, I think that's.
Okay, thank you.
Okay. So I stop sharing.
Yeah,
Thanks.
okay.
Now, we came to the end of this session. On behalf of Bharata Mata College, I would like to thank Dr. Nasin sir for chairing the session. Thank you, sir. Once again, I would like to thank Dr. Vinitha B for sparing your valuable time to be here with us. Thank you, ma'am. Your presence made this day amazing and interesting for us. All are requested to join at the next session at 2 p.m. without fail. Thank you. Thank you.
Thank you.
Recording stopped.